So welcome. So this is first law of thermodynamics. There's a zeroth law, first law, second law. We're going to do the first law. I'm going to talk about things like heat and internal energy. We're going to talk about calorimetry. And then we'll talk about the first law and heat transfer mechanisms. So, okay, let's remember definitions are important to us. And we've talked about these somewhat in the last chapter, but let's just look at them again. Internal energy, sometimes called thermal energy, both terms are used, is all the energy of a system that is associated with its atoms and molecules. If you like, it's the energy that's inside the object. It's not, I don't increase its thermal energy simply because I give it more potential energy, although the object now has mechanical potential energy. I don't increase its thermal energy because I put it in my car and drive it at 60 miles an hour, even though now it has mechanical kinetic energy. It's only the kinetic energy of and the potential energy of what's inside, the atoms inside, and relative to each other. So if you like, the frame of reference is relative to the object, so you can't cheat by moving in a gravitational field or making it go faster. So when viewed from a reference frame at rest with respect to the object, a sample's temperature is directly related to its internal energy. So when your internal energy changes, your temperature changes. And when your temperature changes, your internal energy changes. And I didn't get that for the longest time. And it's obvious. It's so obvious they didn't bother putting it in big letters in the book, so I missed it. And it's like, it's really valuable. So that's the first thing, internal energy. And then heat. Heat is transfer of energy across a boundary of a system due to temperature difference between the system and its surroundings. You know, the spoon and the ice cube and all that kind of stuff. Work. Oh, work's going back to mechanics. Work is the transfer of energy across a boundary of a system due to mechanical manipulation, such as compression or expansion. That's interesting. We're bringing in something mechanical to something that's been thermal. And we're going to find out that now we're linking together the mechanics we learned and the bit of thermal that we've learned. The SI unit for heat is the joule. Hold on, what about all that calorie business? That was when we didn't really know what was going on. We'd take water and we'd heat it up and we'd say how much energy is needed to heat this water through a certain temperature change. That's heat, we'll call that a calorie. And they even thought about having a caloric fluid. They thought hot things contained a caloric fluid. And when they cooled down, the caloric fluid was leaking away and going somewhere else because other things got hot. It makes sense. And, you know, if you think about it, it doesn't have any more mass, but it's got caloric fluid inside it. Well, that's a bit suspicious, but well, it works, and it does work. Trouble is, you can never find a bucket full of caloric fluid. So, does it work? Well, it's a simple model for simple situations, but we've gone past that now. Now we prefer not to think about it because there's no need. Because now we realize that internal energy is energy. And energy is basically measured in joules. So we say the SI unit for heat is joule. The traditional unit for heat is the calorie, the little calorie, which is the amount of heat needed to raise the temperature of 1 gram of water by 14.5, from 14.5 to 15.5 degrees C. That's just so that everybody in the world can do it. It's not because there's something special about 14.5 to 15.5 degrees C. It's just so that let's specify it. Let's not make it too close to freezing. Let's just make it nice and in a range. And then the energy content of food is sometimes measured or often measured in calories, big C calories, which is the killer calorie because there's 1,000 of them. And I'm a bit cynical, and to my mind, if you put on the side of a Snickers bar that it contained 240,000 calories, even I'd pause before I ate it. But if you put down it's 240 calories, I go, oh, it's only 240 calories. How much is that? That's no big deal. It's a massive amount of energy. Try if you want to know how much energy it is, let's make it easy. Take rather than a gram of water, take a kilogram of water, which is what, a litre, okay? Is that right? Yeah, that's right. Take a kilogram of water and take like 2 spoons and rub them together until the temperature rises by 1 degree. And then let me know how you feel at the end of that, because you will be exhausted until it raises by, and that's the work done in that's the work done in a kilocalorie. It's an amazing amount of energy. Watch out. In this class, I tend to deal in joules. I might ask you for a conversion. It's a great opportunity to test if you remember the factor label technique. But watch out when you're out and about. If you buy food from Europe, it'll probably be in kilocalories, and if you buy food from the States, it'll probably be in just big calories. There's also a thing called a BTU, which is the energy required to raise 1 pound of water by 1 degree Fahrenheit, I think it is. And unfortunately, different traditions, different industries have different traditions. So you will find BTU used in things like furnaces and the like. They'll talk about BTU. So it's not like you're never going to see BTU. It's not like you're never going to see little calories. It's not like you're never going to see big calories. They're just around. But we tend to work in joules, which is the smaller unit. I'm giving you some help here. So 1 calorie is that many. So it can't be that, can it be? It can't be that, because that's, one of them is 1,000 of them. And let's have a look. 1 calorie is that, so it can't be BTU, because the BTU is worth 252 calories. So now we got down to calories and joules. And notice 1 calorie is 4.8 joules. So which is the smallest one? The joule. Now, visually, what is a joule? Use an apple to demonstrate to me a joule.
Use a what?
An apple.
Use an apple to demonstrate.
Yeah, think about work.
Lifting it up from the ground.
Lift 1 apple up from the ground. How high?
5 meters. Until you've consumed the joule.
Yes, I know.
5 meters.
But how high would that be? No, it's not. How high?
3 meters.
1 joule equals 1 Newton meter. A Newton is an apple. That leaves a meter.
1 meter.
So from the floor to the desk, a nice apple, that's 1 joule. Okay? Yeah? So you want a calorie, a little calorie? 4 apples. You want a food calorie? 4,186 apples. That's how much work it is. So think of joules in terms of newtons and apples, yeah. Use factor label method to convert. So we're going to do this. Do you remember this? 17 BTU. But I don't want BTU. I want joules. So I got to look at my conversions. And I have BTU, so I'm going to go from BTU to little calories. And I'll go from little calories to joules. I don't need to worry about this big calorie stuff. Yes?
On the test, would you also be giving us these conversion things?
Yes, I would, yes. So, 17 BTU, and I don't want BTU. So we go BTU, and we go little calories. And you go, well, 1 BTU is 252. Cross out my BTU. But I don't want little calories. I want joules. So put the calories on the bottom. And 1 little calorie is 4.186 joules. And that equals, I don't know, what does that equal?
17932.8.
There we go, 17933 joules. So it's just a nice little thing to say. I wonder if they remember how to do this guy. Show the 80 kilogram teacher. So there's a little story behind this with my wife married me right at the end of my kind of like youthfulness. I was mid-40s, and you can go, how you go, there's a big difference between a 16-year-old and a 19-year-old. You won't confuse them. But a 19 and a 22, you can't really tell. There's this plateau you're on in your early adulthood. And it goes on until about 35. Then you get to 35, another little plateau until you're about 45. And it's downhill from there. Okay? So she met me when I was about 45, and I was still kind of sporty and all that kind of stuff. And then we got married. She was divorced, which really helps. For someone like me, it's kind of like, because she had her first husband had done was a bit of a piece of work. And so I was like, just being normal, I was like exceptionally nice. It was great. So so we got married, and it was like bliss, bliss, bliss. I was getting decent food for like the first time ever, because my cooking was pretty awful, but it was great. And I started putting on some weight, and then after a while, my wife said to me, sweetie, I kind of preferred the sporty Tony rather than the, I want a second, helping of dessert Tony. I said, don't worry, I got it all taken care of. And she said, why? And I said, you work on the 4th floor of your building. I'm just not going to get the elevator when I come and meet you for lunch. My wife's really smart, and she goes, let's work out how much energy you burn when you or put it another way, you have a Snickers bar, let's work out how high you have to climb. So I want to show that an 80-kilogram teacher would have to climb that amount of floors, to work off this thing. So
She literally made the equation and calculated it out.
She made me do it at the board. So 250 calories. And let's have a look. I want to convert this into, let's go to little calories first of all. And 1 big calorie, that's the killer there. There's 1,000 of them. And the big calories are gone. And then I want to go to joules. And what was it? It was, which way around was it? The joule is the smaller one. So 4.186, and that's 1. So I got rid of that. So that's how much, and then that's my work. So that equals my work, which equals my force times my distance. So this is going to equal my force, where it's going to be 80, that's my mass, mg, times 10 times my distance. Piece of cake. So we go 250 times 1,000 times 4.186 Z. I want to convert from mass into newtons. Yeah, force. So force is equal to mg. So that's going to be 80 times 10. I've done something wrong here. So 250 calories, 250,000. Oh no, I'm not. No, I'm just been a bit apprehensive. So that's going to be that on the left-hand side, by the way, is about 1 million. So that's 250 times 1,000 times 4.186. So that's going to be 1,046,000, whatever it is. So that's going to be 104,6500 over 800, which equals divided by 800, which equals 1,380 meters, which is about, by the way, it's about 4,000 feet. So if you could convert all that energy into useful energy, you could launch me 4,000 feet in the air using a Snickers bar. This is like huge stuff, which is about 325 floors, or several times up and down the Empire State Building. To work this thing. By the way, that is, maybe on the back side of Snickers bars, it shouldn't say 250 calories or even 250,000 little calories. It should say 1,000,000 joules.
Somebody would buy it.
1,000,000 joules. I would. But...
Still buy it.
Okay, so a bit of a break. Let's look at calorimetry now. How many people have done chemistry part 1?
Long time.
Sometime. Chemistry is sometime. Most people have done physical sciences.
Yeah.
You did calorimetry?
Some point,
Yeah. Okay. Most substances go from solid to liquid to vapor when we heat them up. And some substances sublime. They go straight from solid to vapor. Actually, a lot of substances will do that if you can change the pressure that you're working at. But things like cobalt, if you heat cobalt up, it just sublimes. It just goes and sublimes. But we're not going to deal with stuff like that. We're going to deal with stuff that genuinely reaches its melting temperature, melts, heats up again, reaches its boiling temperature, vaporizes, heats up some more. So we're going to deal with that. If I plot temperature versus energy added, then my initial energy will be just taking the solid to its melting temperature. And then when it all is at its melting temperature, I melt it. And then when it is all melted, I heat up the fluid and take that to its boiling temperature. And then when it is all at its boiling temperature, I vaporize it. And then when it's all vaporized, I can heat up the vapor. So these steps, these steps. This diagram is important because it enables you to figure out what's going on in calorimetry studies. This diagram for water is very inappropriate. It should be a graph that looks like that, and it should be a little, and then it should be a really long thing, and a little, and a really long thing, and a little. Real big plateaus, real small slopes. Takes much more energy to go from one end of the plateau to the other than it does to go from your freezing point to your boiling point. The slope segments are, the slope segment A, C, and E depend upon a thing called specific heat, and that is how much energy you need to change temperature. And the width of the sections B and D, they're the plateaus, depend upon latent heat, how much energy it takes to change the phase. Phase means state, physical state.
What's the latent heat?
Latent heat is the amount of energy it takes to change the phase, the change from solid to liquid or liquid to gas. So we can have the heat capacity. For a substance, we care about heat capacity. How much heat capacity is in this thing? I'm sorry, I misstated that completely. For an object, an example, a sample, I care about my heat capacity. How much energy does it change to change this block from 10 degrees to 20 degrees? For a substance, I care about specific heat capacity. And frankly, I'm going to be on this side of the table all the time. Yes?
What's the Q stand for?
Q is, I'm going to get to that. So Q is the amount of heat. So specific heat capacity is the amount of energy needed. There's my Q. To raise the unit mass, there's my M. By 1 degree, there's my delta T. Okay? It's not the temperature, it's the temperature change. Yeah? It is the mass, it is the heat, but it's the temperature change. So I learned this really well. And typically I'll be working in joules per kilogram Kelvin or joules per kilogram degree C, because they're the same thing. Sometimes in old books they'll talk about calories per gram degree C, or maybe in engineering you might talk about calories per gram degree C. What is the specific heat capacity of solid gold that takes that amount of energy to raise the temperature of that amount of stuff by 6 degrees C. So here's my stuff. What do I know? I'm going to add heat. So my delta Q is going to equal, yes, 3096 joules, and my mass is equal to 4 kilograms, and my delta T is equal to 6 degrees Celsius. So I say my C is equal to Q, sometimes delta Q, because it's the amount of heat, or the heat change, over M delta T. So this is going to be 3096 over 4 times 6. C is equal to 3096 over 24, which equals 3096 divided by 24 equals 129. 129 joules per kilogram degree C. So there's a thing on specific heat. Consider putting a 1 kilogram sample of a high specific heat material. That would be like water. Well, concrete. There's a good example of a solid high specific heat material. And a 1 kilogram sample of a low specific heat material. Low specific heat like aluminum or copper or something like that in an oven. Both materials start at room temperature and end at the oven's temperature. Which material will heat up faster? Ask yourself. Assume the energy can get in just as easily into each one. So which one will get the energy it needs to raise its temperature sooner? The high specific heat, which takes a lot of energy to change its temperature by 1 degree, or the low specific heat? So that's just near the end, so I'm going to just, it's low. High specific heats are great. They don't change their temperature even if you get more sunlight on them or less sunlight on them. They're great. Low specific heat materials are great. They heat up really quickly. You want to make a frying pan, make it out of something that's got a low specific heat. You want to make an energy storage system, make it out of something that's got a high specific heat. Yeah? Because although the low specific heat will get to its temperature faster, when both are at that temperature, the high specific heat contains so much more energy. I lived in the north for a while, and in some of the offices there, they had, strip heating, communal heating at the side. And in some of the offices, they had these old space heaters, and they were basically put in by the electrical company, and it was basically, there was no on-off switch for them. They heated up at night, and then during the day they turned off automatically by the company. It was on a timer. And so they magically turned on at night, and they magically stayed warm during the day, and they weren't great in the afternoon, but they were okay, And then one day, I guess they were messing with them because they were getting rid of them because they wanted more control. So they broke one, and it was basically a metal can, and inside were 8-inch concrete blocks, and between the concrete blocks was one of those stove elements that you get in an electric stove that you can buy at any hardware store. I could have made it myself. There was a little timer on there. It was like, and the idea was, electricity is expensive during the day, so if we can get you to use electricity at night, so much the better. So fine, we'll put the element on at night when no one else wants to buy the electricity and it's cheap, and it'll heat up these concrete blocks. Well, okay, but then during the day we'll turn off the electricity, but the room will only cool down slowly because the concrete blocks contain so much energy. There's a ton of energy, and it bleeds out so slowly that it maintains the temperature in the room really well. So high specific heat materials are great for keeping things at a stable temperature. You heat up, you cool down, basically you're going to stay about the same temperature. Low specific heat materials are great for changing temperature quickly. Okay. So which material will require more heat to reach its final temperature? Well, the high specific heat material, yeah, the high specific heat material. Which will store more energy because of the temperature change? The high specific heat material. So it's not that high specific heat materials are terrible. They're really useful. They're not useful for every application, though. For other applications, low specific heat materials are great. If I have a plot of T and Q, a high specific heat material takes a lot of energy to raise the temperature by a little bit, so that's a high C. And a low specific heat material only requires a little bit of heat, so this is low C. So the slope indicates the specific heat, but it's not equal to the slope.
So there's no difference between the two things?
There's no difference between the two what?
Crystallization and vaporization.
I'm just talking about heating a solid up or heating a liquid up. I've not got to that bit yet. Okay? Now, latent heat. Latent heat crystallization. This is the amount of energy we need to change 1 kilogram of solid into a liquid without changing its temperature. So for ice, I would have 0 degrees C ice goes to 0 degrees C water. Now that might seem weird. You might say, well, hold on, it can't be 0 degrees C water because that's ice. Or you can't say it can't be 0 degrees C ice because that's water, but it can. You can have 0 degrees C ice and you can have 0 degrees C water. And latent heat of vaporization goes from 100 degrees C water to 100 degrees C vapor without changing temperature. And of course they can go backwards. So the energy it requires to go from solid to liquid, you can get back if you can solidify something. The energy it takes to vaporize a liquid, you get back if you can condense. This is really fantastic stuff. Your refrigerator works based on this principle. It's great. So what I put in, I can get out, at least most of it, if I'm careful.
Because the energy can be destroyed.
Well, no, but I can get to it, yeah. So what is the latent heat of crystallization? So the latent heat of crystallization, so L is equal to Q over M, which equals 20100 over 300 grams, 0.3 kilograms. So L would equal, what's that going to be? 6 3s are 18. It's going to be that guy, 6700. Yep. So 67000 joules per kilogram. Now, what was a joule? A joule was lifting an apple onto a table. Yeah? This is lifting 67,000 apples onto a table to melt 1 kilogram of gold. That's a lot of apples. Okay. They're real numbers, by the way.
And isn't gold as one of the easier ones to melt?
Sorry?
Isn't gold as one of the easier ones to melt? Like the less?
I suspect you're right. No, I think you're right, actually. I might be. Yeah, yeah. Well, it's yeah. Okay. Okay. Calorimetry. Oh, sorry. So the width of your plateau depends upon the latent heats. Calorimetry. there's 3 levels of calorimetry. I have the liquid and a solid like brass and a liquid like water. And I mix the two together. I immerse the solid in the liquid, and the temperature of the liquid equals the temperature of the solid in the end. So that's calorimetry with no phase change. Then I can have ice cube and water, and over time the ice cube melts. But it's the same substance. That's phase change, yeah? And then the third level is I have butter with oil. And then over time, I get melted butter in the oil. Not the same stuff. 3 levels. Okay? Calorimetry. In an isolated system, the heat lost by one element equals the heat gained by another element. I actually prefer to say that delta Q is equal to 0. The change in total heat is equal to 0. Yes?
Does the bar flow down the top or no?
I'm sorry?
In the third one, does the bar flow at the top or no?
It doesn't matter. But you can, if you like, you can assume it does. Example, a 4 kilogram, 20 degrees C sphere. Oh, wonderful. With a C equals 8 joules per kilogram degree C is dropped into a calorimeter which contains 6 kilograms of 10 degree C fluid with a C equals 4 joules per kilogram degree C. I want to know the final temperature. On these, I tend not to use realistic numbers. Maybe in the homework I'll use realistic numbers, but for a test I'll use very simple numbers for specific heat and the like. In this case, what's happening is the heat given off by this guy is absorbed by the fluid. So I say delta Q is equal to 0. I can say the mass times the specific heat times the temperature change for the solid plus the mass times specific heat times the temperature change for the liquid is equal to 0. I look at my diagram. I go 4 times my specific heat, and my specific heat in this case is 8, times my temperature change. The temperature change is always T final minus T initial, and the T initial for that guy was 20. Plus the mass times the specific heat, the mass is 6, times specific heat, which is 4 for the liquid, times the temperature change, and the temperature change is always T final minus T initial, which is 10 in this case. So this will be 48 times TF minus 20 plus 24 times TF minus 10. That should be 32.
4 times 8.
4 8's 32. Let's look at the 4 and look to the 8. Thank you. Got a question or a comment?
Yeah, question. Where'd you get the limit for the MC delta T?
Because we said that C is equal to delta Q over M delta T. Sorry, that's the specific heat equation. Yeah. Now, let me ask you, is the final temperature going to be more or less than 20? It's going to be less than 20. So that means that I'm going to have a negative number for this side, yeah? And will the final temperature be more or less than 10? So that would be a positive at that. So can you see how the negative and the positive make 0? Okay. It just takes care of itself. So I go 32 TF minus 640 plus 24 TF minus 240 equals 0. So that's going to be 56 TF is equal to 880, if I did that right. So TF is equal to 880 over 56, which equals 880 divided by 56 equals 15.7. There's my answer. So some of you may have been trained the way I was trained, where you were told that heat lost equals heat gained. And then you had to mess with your final temperature and your initial temperature to make sure you always had a positive, and it was a bit of a mess. This works out, I think, much better because you just put the final temperature minus the initial temperature and you get the answer. That's the first level of calorimetry. Next time, we're going to do some of the second and third level problems, but we'll come to this next time. Okay. Just 1 second.